Alright, so here's the video for section 1.7 on linear inequalities and absolute value inequalities. Now, the linear inequality part will be mostly review, I would think, and we've been doing some of this in class for a while now. The absolute value inequalities may be something you haven't seen before, or at least haven't seen for a while. So what we're going to try to do in this section is, first of all, use interval notation and find intersections and unions. Now this is going to be a review because I spent some time at the beginning of the semester going over these things. Then we'll do a couple examples solving linear inequalities, and then look at some compound inequalities and absolute value inequalities. So basically, solving an inequality, it's like solving an equation. But now we're trying to find a set of numbers that make an inequality a true statement. Of course, we're looking for solutions that make the satisfy the inequality, which means make it true. And like with the equations, we call these set of numbers the solution set. So a brief review on interval notation. The open interval from A to B, notice open means we have parentheses. It's the set of numbers, it's a set of all x values, and where x is strictly in between a and b. So these inequalities are strict because it's an open interval. And then a closed interval, which we have brackets around, it's the set of all x values where x is in between a and b, but these inequalities are not strict. X is going to be greater than or equal to a, and less than or equal to b. And we have infinite intervals. The infinite interval from a to infinity is all x values that are strictly greater than a. Or we can have an infinite interval where it's half closed. Remember, around the infinity, on the positive or negative side, it's always open. You can't include infinity. But if we have a bracket, this is going to be all the x values that are less than or equal to b. This is reiterating what I said before. Parentheses are endpoints that are not included, and brackets are endpoints that are included. And we always use parentheses around positive or negative infinity. So if you want to try to express this interval in set builder notation, well, this is going to be equal to the set of all x such that what has to be true about x? Well, x is always going to be greater than or equal, and it's greater than or equal because I have a bracket. It's greater than or equal to 1, and x is less than or equal to 3.5. Okay, so that's the closed interval from 1 to 3.5 in set builder notation. And then we have this open interval, negative infinity to negative 1. Well, any number that's in this interval, the only thing it has to be is smaller than negative 1. So in set builder notation, this is going to be the set of all x such that x is strictly less than negative 1. And that's all there is to it. So finding intersections and unions. So just recall again, intersection is what two sets have in common. And union is what you get when you take two different sets and you put them together. So let's look at two examples. So if we want to find the graph of these two sets, the graph of the set closed interval -1 to 1 to 3 intersection 2 to 6, and this upside down U means intersection. We can look at the graph of the graph of 1 to 3 and the graph of 2 to 6, and then just see what both of them have in common. So let's do that. So I'll pause the video to draw those two graphs, but here I have a number line and I'm going to shade in the closed interval from 1 to 3. So it's a bracket, so from 1 to 3. And I'm also going to shade in the open interval from 2 to 6. So here's 2, and here's 6. So I have those two intervals. And then to see what they have in common, I'll draw another number line down here. So here's 1, 2, 3, 4, 5, 6, and 7. So what do these two intervals have in common? Well, the only thing they have in common is going to be this bit right here. Okay, so we know it's just going to be from 2 to 3. So the question becomes, do we use brackets or do we use parentheses? Well, this bottom interval has a parenthesis, so 2 is not included. So when I look at what the two sets have in common, I'm going to have a parentheses right here. But now, on the other side, 3 is included in this one. And since this interval 2 to 6 includes 3, 3 is included in both of them. So I will use a bracket on this side. So if I want to write this as an interval, this is the half-open interval from 2 to 3. And that's what the intersection of closed 1, 3 and open 2, 6 is. Okay, so now solving inequalities. So a linear inequality is one that basically can be put in the form of something that looks like a line on one side. Remember what we said linear equations look like way back at the beginning of the semester. A linear equation is something of the form like this. AX plus B equals 0. So a linear inequality is just AX plus B and then an inequality sign, right? And then a 0 with it. And a really important point that you need to always remember, that always holds, whenever you multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. So let's go ahead and see how we solve this one. Basically, you just want to get x by itself, like you would if it was an equation. So we'll subtract 2 from both sides, and we'll have negative 3 is less than or equal to negative 3x is less than or equal to 5 minus 2. And we can divide both sides by negative 3. Or actually, before we do that, let's go ahead and simplify that right-hand side. So negative 3x is less than or equal to 3. Now divide both sides by negative 3. And notice that since we're dividing by a negative number, that when I write down this last step, the direction of my inequality is going to flip. So this is going to be x is greater than or equal to 3 over negative 3 just gives me negative 1. So that's the solution to this inequality. Now, as far as graphing the solution on a number line, why don't we write it in interval notation first? So this is the set of all x, where x is greater than or equal to negative 1. So the solution is going to be, the interval solution is going to be bracket, because it's greater than or equal to negative 1 to infinity. And then if you want to try to graph that, it just looks like this. It's negative 1, 0, 1, 2, and so on. And then if we shade it, it would be bracket at -1, and it goes to infinity. Here's a little bit more complicated looking one, and you can tell from the heading that this guy is not going to have any solutions. Or maybe it'll have all number solutions. Let's solve this one and see what happens. Okay. So first thing we need to do, we're trying to isolate x, so we're going to distribute the left-hand side, and we'll get 3, oops, let me not use that color. We'll get 3x plus 3 is strictly greater than 3x plus 2. So if we want to get all the x's on one side and the non-x's on the other, subtract 3x from both sides. So we'll have 3x minus 3x. And we'll also subtract 3 from both sides. So what we'll end up with is this expression. So 3x minus 3x is just 0. So we're saying that 0 is greater than -1. Well, look, we have an expression that doesn't have any x's in it whatsoever. So what does that mean? It means no matter what value we plug in for x, we're always going to get a true statement, because 0 is always greater than -1. So the solution is all real numbers, or as an interval, -infinity to infinity. Whenever you end up with something like this, this is called an identity. Okay, or I'm sorry, this isn't called an identity, this is just a true statement. 0 is always going to be greater than -1, and that'll happen independent of the value of x. So the solution is all real numbers. So I'll put in another example here so I can show you what happens if you get one that doesn't have any solution. So if we want to try to solve this inequality, 2 times x plus 1 is greater than 2x plus 3. Well, we start the same way. We'll distribute the left-hand side, and we'll have 2x plus 2 is greater than 2x plus 3. So if we subtract the 2x from both sides, we're just going to have 2 is greater than 3. But this is false, right? 2 is never greater than 3. So if you ever try to solve one of these, you end up with a false statement like that, like 2 is greater than 3, or 0 is greater than 1, or something like that. It means that there's no solution. There's no x that we can plug into that initial inequality to make that a true statement. So that's what would happen if you had an inequality with no solution. All right, now compound inequalities. The idea is really the same, but instead of having a single inequality like 2x plus 3 is less than 11, or 1 is less than or equal to 2x plus 3, we have two different inequalities in there together. And the way this works is just like solving a single inequality. Whatever you do to one part, the left, the middle, or the right, you do everywhere. And the goal is still the same. We're still trying to isolate x. So what would we have to do here to get x by itself? Well, there's that plus 3. So if we start out with 1 is less than or equal to 2x plus 3 is less than 11, first thing we need to do is subtract 3 everywhere. So I'm going to subtract 3, subtract 3, subtract 3. And 1 minus 3 will leave us -2 is less than or equal to 2x is less than 11 minus 3 will leave 8. Okay. And now to finish getting x by itself, we'll divide everywhere by 2. And that'll leave us with -1 is less than or equal to x is strictly less than 4. So this is the solution to our inequality. And if we wanted to graph that on a number line, it would just look something like this. So here's -1, 0, 1, 2, 3, 4. So -1, 0, 1, 2, 3, 4. And then how do we shape that? Well, the x's are greater than or equal to -1, so I have a bracket, and they are strictly less than 4, so I have a parentheses. So those are what the solutions look like. And just for fun, let's write the interval notation for this. It's the interval from -1 to 4. So that's how you solve compound inequalities. You do it just like one that has a single inequality sign, but whatever you do to one part, you do to all of it. And now, all of that stuff probably was a review. You've seen before either in high school or here in Math 989 or 999, but this is where people tend to forget a little bit. It's solving absolute value inequalities. And what you have to pay attention to here is what your expression looks like. You always want to put it in this form, where you have the expression with the absolute value on the left and the part that doesn't have an absolute value on the right. See, here we have an absolute value on the left, doesn't have an absolute value on the right. And if your expression is the absolute value of something is less than, well, then you're looking for numbers that are going to satisfy this expression. Because remember what absolute value really is. It's the distance from 0. So if the absolute value of u is smaller than c, that means u is within c units of 0. So it's going to be bigger than -c and smaller than c. On the other hand, if your expression is the absolute value of u is greater than c, I'm saying that u's distance from 0 is bigger than c. So u is either going to be less than a -c, because then it would be more than c units from 0, or u is going to be bigger than c. And these are the two ways that u can be more than c units away from 0. And of course, these rules still work if instead of less than, we have less than or equal to, or instead of greater than, we have greater than or equal to. So let's see an example of how this works. So we want to solve and graph the solution set to 18 is less than absolute 6 minus 3x. Well, look, this isn't in the right form, okay? We want to get this in the form where we have an absolute value on the left side. And the equivalent expression would be 6x minus 3x is greater than 18. Okay, because look, we're saying that 18 is smaller than 6x minus 3. So if we reverse the way that's written, 6 minus 3x is bigger than 18. Now, since we're saying 6 minus 3x is bigger than 18, when we try to rewrite that, we need 6 minus 3x to be more than 18 units away from 0. So what that would look like is 6 minus 3x is either smaller than -18, or 6 minus 3x is larger than 18. So we need to solve these two inequalities separately. So let's do the one on the left first. I'll subtract 6 from both sides, and we'll have -3x is less than -24. Divide both sides by -3. I'm dividing by negative, so my absolute value changes direction. So I'll have x is greater than, strictly greater than, -24 over -3 gives me 8. Okay. So as long as x is bigger than 8, my inequality is satisfied. On the other side, I'll subtract 6 from both sides, and we'll have -3x is greater than 12. Divide both sides by -3. My inequality sign will flip again, so x is less than 12 divided by -3 is -4. Okay. So I also have solutions if x is less than -4. So what do these two solutions look like as intervals? Well, x greater than 8 is just 8 to infinity, and x less than -4 is negative infinity to negative 4. Okay, so if x is in either one of these two intervals, then it's a solution to the inequality. So if I want to write this as a single interval, the solution, the interval of solution is, well, I would use a union. It's negative infinity to negative 4 union 8 to infinity. And then on a number line, what does that look like? Let's see, I can make this negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see, this is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, negative 2, negative 4, this one will be negative 5. So if I were to highlight a solution, it would be negative 4, or negative infinity to negative 4, or anything from 8 to positive infinity. So that's how you would graph the solution set. So the solutions to this inequality, whoops, let me make that a little bit nicer. The solutions to our original inequality, which was absolute 6 minus 3x is greater than 18, from which we got these two parts. The solutions to that inequality end up being what we have down here. The interval negative infinity to negative 4 union 8 to infinity, and this is what the graph looks like. Alright, that's it. If you have any questions, email me or post them on D2L. Otherwise, I'll see you in class.